All right, let's get right into this explainer tracing the absolute greatest adventure in human history, our journey into the cosmos. We're going to be looking at the hardware, the history, and most importantly, the people who actually make spaceflight possible. We'll see how our reach has steadily expanded step by step from our home planet way out into the unknown. That's one small step for man, one giant leap for mankind. We all know those legendary words from Neil Armstrong in July 1969. But that single, awe-inspiring moment, it didn't just happen in a vacuum. It was the result of decades of breakneck technological evolution, and it laid the absolute foundation for everything we're doing in space today. Here's our flight plan for today. We'll start with breaking Earth spawns, move into forging space explorers, check out our orbital outpost, talk about returning to the moon, and finally, look ahead to the interstellar horizon. Section 1. Breaking Earth's bonds, the breakneck speed of early spaceflight. Let's look at how fast things actually took off. Just look at this timeline. The beginning of our journey wasn't a slow crawl, it was an absolute sprint. We went from a German V-2 rocket barely kissing outer space on a suborbital flight in 1944 to Sputnik 1 orbiting the Earth in 1957. 4 years later, bam, Yuri Gagarin is up there, the first human in space. And a mere 8 years after that, we're literally walking on the moon. Going from the first suborbital hop to footprints on another world in just 25 years is a staggering testament to human ingenuity. But here's the thing. This wasn't just chaotic random experimentation. It was driven by a master plan known as the von Braun paradigm. Wernher von Braun, one of NASA's foundational minds, mapped out a logical, stepping stone approach for us. You build multi-stage rockets, then you establish a space station, then you go to the moon to build bases, and ultimately, you use that setup to colonize Mars. Now, sure, Apollo kind of skipped the space station step to get to the moon first, but this core paradigm, it's basically been the blueprint for NASA's strategy for decades. Section 2. Forging space explorers, preparing humans for the cosmos. Because, getting the rockets to work was really only half the battle. The contrast between how we trained the original Mercury 7 in 1959 and modern astronaut candidates, or A-scans, is wild. Back then, they basically used brute force physical conditioning, strapping those test pilots into massive centrifuges and orbital attitude simulators to test their absolute limits. Fast forward to today, and it's highly immersive and tech-driven. We're talking physics engines, the Charlotte robot, advanced VR headsets, and countless hours in underwater simulations to master microgravity. Speaking of underwater training, you have to understand the sheer scale of the Neutral Buoyancy Laboratory, the NBL down in Houston. Calling this thing a swimming pool is a massive understatement. It's 62 meters long, 12 meters deep, and holds 6.2 million gallons of water. By carefully balancing weights, it perfectly mimics weightlessness, so astronauts can practice spacewalks on actual, life-sized spacecraft mock-ups. They even wear VR headsets underwater now to make it feel exactly like floating in the vacuum of space. And why does that VR integration matter so much? Space motion sickness. Without gravity telling your brain which way is up, your spatial orientation just goes completely haywire. We're talking 60 to 80% of astronauts getting hit with severe nausea and cold sweats. But by using modern virtual reality training, they've actually reduced those nausea symptoms by 53%, and astronauts can perform tasks 12% faster. It is a literal game changer, using tech to solve complex biological problems. Section 3. Our orbital outpost, living and working on the ISS. Let's see where these astronauts actually go today. So, we move from the NBL up to our permanent foothold in space, the International Space Station. It's an incredible web of specialized, interconnected modules built through international cooperation. You've got Destiny, the US lab for Earth and Mars research, the European Columbus lab for fluid physics, and Japan's Kibo lab for life sciences. Then there are the Harmony and Unity nodes, linking it all up and giving the crew a place to eat and sleep. Imagine wrapping up a long shift of fluid physics research and just floating over to the cupola's 7 windows to stare down at the Earth. Absolutely unreal. But surviving up there isn't just about doing cool science and staying physically safe. Psychologically, it's what experts call an isolated and confined environment, or IC, which generates immense stress. To handle that, the ISS uses a fascinating program called the Virtual Space Station, or VSS. It's basically a behavioral conflict management system, featuring modules that guide astronauts through virtual therapy sessions. It helps them manage stress, depression, and interpersonal dynamics, which is absolutely crucial when you're locked in a tin can with the same few people for months on end. Section 4. Returning to the moon, The Artemis era. Having mastered low Earth orbit, we are looking outward again. Let's look at how our launch hardware has evolved to get us further out. This table really breaks it down nicely. We had the legendary Saturn V, the brute force rocket that took us to the moon for Apollo. Then the space shuttle, designed for reusability and building the ISS in low Earth orbit. But today, we're leveling up again with massive new rockets. NASA's Space Launch System, or SLS, is purpose-built to push heavy payloads into deep space for Artemis. And right alongside it, you've got commercial heavy hitters like SpaceX's Starship, aiming for Earth orbit, the moon, and eventually Mars. And the immediate target for rockets like the SLS is the Artemis program. But Artemis isn't about planting a flag and coming right back. The goal this time is the Artemis Base Camp. We are establishing a permanent human presence on the moon. Going all the way back to the von Braun paradigm we talked about, the moon isn't the finish line. It is the ultimate stepping stone. It's the testing ground where we figure out how to extract resources and actually survive long-term before we push even further.
Section 5, the interstellar horizon, Mars and beyond. Let's cast our gaze into the deep future.
So if the moon is the stepping stone, what happens when we reach Mars? Well, hauling heavy steel structures all the way to Mars is incredibly expensive and practically impossible. So researchers are looking at biology, specifically Myco-Architecture, literally growing our Martian habitats out of fungal mycelium. You send a lightweight, inflatable mold, the outer layer fills with local subsurface ice to block radiation, the middle layer holds a nutrient substrate, and the inner layer, you just introduce spores, and the fungal mycelium rapidly grows to create a rigid structural shell. We could literally grow our homes on another planet. How crazy is that? But honestly, just getting to that fungal habitat is a monumental hurdle. You're looking at being trapped in a tiny crew capsule for up to 9 months straight just for the transit. Take the isolation we talked about on the ISS and multiply it exponentially. It's like being stuck in a submarine for almost a year with zero chance of a quick trip home. Solving the extreme psychological challenges of that confinement is just as critical as the rocket engines themselves. And what if we want to go even further, to distant exoplanets? That's where we hit the hard wall of human lifespans. Enter the Generation Ship. This is a conceptual spacecraft built for multi-generational interstellar travel. The idea here is that the journey takes so many hundreds or even thousands of years that the people who finally arrive at the destination won't be the original crew. They will be their distant descendants.
Managing a generation ship is a mind-boggling concept. You're basically maintaining a permanent, self-sustaining human colony in the vacuum of deep space. You'd need to carry hundreds, probably thousands of people, just to ensure enough genetic diversity and actually survive. To conserve resources over those vast stretches of time, a huge portion of the crew would likely be in cryogenic suspension. You'd rotate waking shifts to minimize the crushing psychological toll, making sure there's always a caretaker crew maintaining the ship while the rest of the colony sleeps through the centuries.
From those very first V2 rocket hops to the mind-bending concept of generation ships, every single step has pushed the boundaries of what humanity is capable of. From the brute force bravery of the Mercury 7 to today's VR-trained astronauts, it's been an incredible ride. So I want to leave you with this final thought to chew on. If ensuring the survival of our species meant you had to board a generation ship, a ship you knew you would never leave, knowing only your great-grandchildren would ever get to see a new sun, would you be willing to step aboard? Thanks for exploring the cosmos with me today in this explainer. Keep wondering, keep learning, and I'll see you next time.